Okay, I have to restart my kernel. Sorry about it. Okay, hopefully it works. Okay, we have train Y. Okay, train Y is not here. To run this again. Okay, we have train X and Y. Alright. And we also need our test X. Okay, we have to know the features of our testing set. So the testing set is basically very similar to this, but are those that is equal to the question marks. Okay, so this is our testing features. Okay, so we call it test X. Okay. Alright, so the next thing we have to do is to import the linear regression library. This library allows us to train the regression model by one click. And to call the library, you do from sklearn.linearModel import linear regression. Okay. And you have to do this step is so-called instantiate the model. So you have to first create a blank linear regression model. Okay, and then after you create the blank linear model, you can start to fit your data. So which is train X and train Y. Okay, so that's it. You have fit your linear model using the two features. And now the next step is to make prediction. Okay. To make prediction, we just do lm.predict and put the test X inside. Okay, remember we have two question marks, which is the two flat that we want to predict the price. Okay, so what the model tells us is the first one is 5,050 millions, and the second one is 1.5 millions, which is not very correct, but that's because we only have a very small training set. Okay, and this is our initial guess, 80 million and 5 millions. Okay, and I think the ground truth is something like 22 millions and 6 millions. Yeah.
Question. Why do the data appears from my computer yours?
Oh really?
Yeah.
What do you get?
I have to check the first one. 3444 and second is 1159.
Okay. Is the set completely the same? Because it has to be the same. One thing to check is do the coefficient check. Okay, this is my coefficients. Do everyone understand what coefficient means in a linear regressions? Okay, so linear regressions is just plotting a linear line based on all the variables. And the coefficients, if it's positive, it means it has a positive relationship between the price and these variables. Let's say our first one is floor. Okay. Well, in this case, it means lower the floor, higher the price, which doesn't really make sense. And the 1, 2, 3, 4. Okay. I'll come to your computer later on to check. Okay, let's say Hong Kong. 1, 2, 3, 4. Okay, the fourth coefficient is 300, so that means if it's in a Hong Kong site, it's 3 million more expensive than in a Kowloon site. Okay. Okay, everyone understand till now? This is a very simple linear regression example. Okay. So after we go through our first machine learning example, I'm gonna go through what's the supervised learning versus the unsupervised learning. So in this graph, you can see there are two identical things, but in this case, the supervised learning has a label. Okay, it is labeled differently than the unsupervised learning. In first case, I'm telling the computer the right answer. And in this case, I ask the computer to figure it out itself. Okay, so what is supervised learning? The best way to think of it is imagine a machine is a blindfolded baby. Okay, this baby is not allowed to touch, to talk, to hear, to listen to anything. Okay, and the only input the baby can get is what you fit to it. Okay, it's just like a machine. Or you can think of it, the only ways of communication is to whisper the instruction and the description to the baby's ear. Okay, you can't see, touch, or listen to the surroundings, and yeah, same thing. Okay, now the task for a baby is to classify orange from apple. Okay, but remember the baby cannot see or cannot touch. Okay, so you have to whisper the features of the orange and the apple. Okay, and the two features they are allowed to tell is color and the texture. Okay, color like orange or red, texture is like brown or soft or hard. Okay. So now I'm handing the baby some apple and some orange one by one. Okay, the first time I handle the orange to the baby, and I tell the baby the fruit is soft, and the orange is the color. Okay, this is an orange. And the second is an apple, so I tell the baby this is hard, and this is red, and this is an apple. And every time I pick up a fruit, I just tell the baby the informations. And finally, how I do the prediction is I give the baby one of the fruit and say, okay, it's red and it is hard. What it is? Is it an apple or an orange? Okay, this is so-called a supervised learning. And what the baby is actually learning is a table like this. So we have some orange and some apple, which is the ground truth. And we have the features of color and texture. And it's all lined up in the table. And in the first 1, 2, 3, 4, 5, okay, first 6 rows, this is our training data. And the bottom 2 rows is called testing data, which we didn't give them the label. Okay. If you further improvise to a computer readable format, it's gonna look like this. So you have the orange column, the red column, the soft column and hard column, and everything is translated to 1 or 0. Okay. And you also have 2 labels, which is 1 or 0. Okay, now you can think of it as numerical questions, because everything is in numbers, and all you need to care is, given this combination of numbers, what output can I give? Okay. Alright, this is basically the supervised learning. So it's supervised because you have the labeled data. You know what is called apple and what is called an orange. and it learned by example, which is so-called the training data. Okay, this is the training data, and okay, it basically learned by inferring a function from the features. So a function is basically given these four numbers, output the final output, and probably you can write the function based on these two numbers and write like an equation, like a simple linear equations out of it. Okay. And everything on the right hand side of this table is supervised learning. Okay. And let's say remember we have a bunch of keywords. We learn about category, classification, etc. But what we had the example is just a regression, which is something everyone knows. And I want to demonstrate a classification example as well. So remember in our previous example, okay, we have a column which is 1 or 0, which is categorical. Okay, and for categorical data, we have to use a different approach to classify it. So, okay, to classify it, we use a decision tree. And to call a decision tree is very simple. It's just sklearn input tree. And you probably don't need to do what's above or what's below. You just do this. And remember our train x and train y. We just do slf.fit train x train y. Oh, sorry. Oh. Okay. Oh, not train y, sorry. Train x, sorry, train y. Oh, okay. Oh, because currently our train y is a price, so you have to do df.expensive. Okay. I think you have to do it this way. Expensive. Okay. Let me try the example to see if it works. Train df is not defined. Okay. Train df equals df dot price not equals to question mark and df. Okay, 1 more minute. Okay, unknown df is df dot price equals question mark. Okay, this should work. Alright, it works. Okay, now this is our prediction given the unknown x. Okay, this is the it works quite similarly as the regression problem. So basically you just fit x and y, and then you do the prediction by putting the unknown features into the model, and it gives you the prediction. And the output is categorical, just category 1 or 0. Okay. But don't worry about how it works for now. Okay. So how about unsupervised learning, which is somehow quite magical. You don't tell the computer what it is, but the computer figure it out itself. Okay. So now we'll talk about unsupervised learning. It's the same setting, so again, it's a blindfold baby. Task is still the same, to classify orange or apple. Okay? And the rules is the same, like the baby can't listen to anything, the only input is you whispering the instructions. Okay, this time, I'll do the same thing. I'll just hand the baby. Okay, the fruit is soft, it's orange in color, the fruit is hard and it's red in color. But this time I won't tell the baby, this is an orange or this is an apple. Okay? So basically what the baby receives is very similar to what we previously have. But we don't have the ground truth. Okay, the answer is blank. Right, but we have all the signals. So we have the signals this way, 1010 or 0101. And now the testing data is given these patterns. Which one is likely to be the other group? And put it to machine learning, is actually the computer is actually finding how many groups are there. Okay, let's say if I tell the machine, okay, there are 2 groups, then it finds the row that are more similar to each other. Okay, so if you compare the white colored row and the colored row, these are more similar, and these are more similar to each other. Okay, and if you tell the computer there are 2 groups, there's actually a mathematical formula to find which ones are more similar. Okay, so the similarity is what the computer looks for to differentiate the 2 things. And this is so-called the unsupervised learning. It's unsupervised because you did not label the data. Instead, it forms a cluster based on how similar the 2 data is. Okay. And one important thing is the baby will never know what is called an orange. Okay, because you didn't teach him that it is an orange. But instead, the baby learns something that is orange and soft. And the baby also learns something that is red and hard. And they are 2 very different things. That's what the baby learns. Okay? And the most common unsupervised learning is called cluster analysis. Okay? So I can show you this graph to show this is supervised and this is unsupervised. Okay? Also, supervised learning tends to be drawing the boundary between 2 groups, while unsupervised is finding which dots are more similar to each other. Okay. Okay, this is an example for unsupervised learning. One of the unsupervised learning is called k-means, and I'm talking about this. So in unsupervised learning, you have to tell how many cluster there are. So in here, I just specify 2 clusters. And after I run it, okay, this column is what the machine figured out. Okay, so it successfully figured out these 2 columns are very different from the rest. Okay, but it didn't classify the first column because the price is like 870, and it is sort of in a boundary. So the model classify it incorrectly. Okay. So Okay, the next thing we'll talk about is a regression. Okay, basically this is like test. Okay, if you refresh the dots, okay, you can just try to plot your own regression line. Okay, what regression means is find the best fitted line out of all the dots, and you can keep on trying to find if it's the best fit line. And once you click this, it will show you which is actually the mathematical optimized line out of all the dots. Okay. If you are a bit confused in this case, you can think of the x-axis is price and the y-axis is one of the features. And you can plot everything on the dots. And once you draw the straight line, then you can have one side being unknown and able to find the price. Okay. And that's regressions. And to help you visualize what exactly is a regression, let's say now I'm doing a test with you. I want to throw a ball. Okay, I can throw a ball whatever whatever strength I apply on the ball, and the stronger I throw, the further away the ball goes. And after a lot of trials, this would be my relationship. Okay, because the harder I throw, the further away the ball can go. And these are all the record of where my ball lands. Okay. And if you recorded this ball and that ball, so this ball I throw it in a degree of like 2 and then it reached 21 meters. And in here I throw it with a degree of close to 10, I throw it to 36 meters. Then you can somehow draw a straight line out of all the dots. But now you might think of a question like, what is so-called the best fit line? How do computer come up with the best fit line? It's actually quite simple. Let's go back to this example. So how would you draw the best fit line in this case? Okay, you just probably do it by hand, look at it, and alright, it looks quite fit. So this is my best fit line. But the computer usually beats you, and the computer calculates the best fit line by calculating the minimized sum of error. Okay. So what actually a computer does is it does it very similar to a human. It just keep on trying the line. Okay, you can try it like this, like this, like this. Okay. But for every line, it calculates the vertical distance between every point and the line. And if the overall distance between the lines is minimized, that means whenever you move it, it only increases the error. And in that case, it reaches like a local or global minimum. And that's the optimized positions. If you watch the YouTube video I sent out, this is how the machine works. So let's say you're on a mountain called the Mount Everest. So the higher the mountain is, the more error it is. What the algo does is it keeps looking around to find the movement that minimizes the next step of error. So if the machine starts placing the line with this degree of error, it will always look for the direction of moving the line in a way that it has a lower error. So it keeps on decreasing the overall error until it reaches the minimum. If you care about the mathematical formula, this is how they do it. I don't really care, but you can like go Wikipedia. And this is what I meant by minimizing the least sum of squared errors. Okay, this vertical distance is the error, and what I do is just minimizing the overall sum of it. Okay. Okay, this one is decision tree. I'll see what I have in here. Okay, this is a very good visualization for a decision tree. Once you keep on scrolling, the right hand side shows some animations of what's actually going on in the algorithm. Okay, so if you read it, this is again the house price in San Francisco, and this is the distribution of this is the distribution of how the house price distribute in New York and in San Francisco. Okay, I think green is New York. Okay, sorry. Green is New York, and this is this is San Francisco, and this is New York. Okay, so it means the flat in San Francisco is a lot bigger than the one in New York. And this is the distribution of the area and this price per square, comparing between New York and San Francisco. Okay, this is just a pair plot everyone should know about by now. And we have a lot of different variables like elevation, years built, how many bedrooms, price, etc. And you see a lot of distribution. Okay, but now my task is to separate the two types. Okay, given an unknown flat, I need to tell you this is from New York or this is from San Francisco. Okay, and I know the ground truth for part of it, but for the unknown data you want to predict, I don't have the ground truth. If you stare at this this graph, let's say this is the area, like how big is the flat? Okay, this is San Francisco, this is New York. What's the best rules that I can come up with to differentiate the two? Okay, it is quite obvious, right? The larger the flat is, it's more likely to be San Francisco. And there should be a line that separate the two. Okay, if you go back up. Sorry. We should be able to come up with a rule that every flat that is smaller than 339 feet can be from New York. Otherwise, it's from San Francisco. Okay, that's one of the rules and one of the cutoff line we can find. All right. And after we find this cutoff line, we still have like a bunch of San Francisco flat that is being unclassified. Then you can keep on going through the rest of the variables and try to find out, is there a boundary that I can classify the two things? Okay. And if you go through every single variables and do the split, eventually you can draw a tree like this. So first of all, I split by how big the flat is, and then I split by one of the price, and then I split by which year it was being built. Okay, and if you look carefully, the variables can be reused. Okay, and I keep on finding the boundaries and the best point of split. And eventually I built a very complicated system that have a lot of rules to split and differentiate the two things. And this tree is so-called our decision tree model. And let's say if you have new incoming data, you will just keep on classifying and keep on going through every single rules and to decide which side it is. Okay. And in here, because we are using our training sets, so the accuracy must be 100%. So if you do it with the testing set, you can see some part of the houses are wrongly classified, and some part of the houses from the San Francisco side is actually from New York. Okay, but we have successfully built a model that classify 90% of the cases. Okay, and this is how a decision tree works. It's basically splitting the two groups by finding the criteria. Okay. Does it make sense? Or if it doesn't make sense, just try to look through these animations, and this is quite intuitive. And again, this is one of the example in the YouTube video again. If you don't understand, you can go back to the YouTube video. But let's say I have three apps right now, and then I have two features, which is the gender and the age. And now I have to find the best split to predict which customer will buy which app. And in this case, if I do a split on age, like everyone below 15 years old will buy Pokemon Go, and I split it by gender, everyone who is female will go to buy WhatsApps, and otherwise it by Snapchat. That's sort of like a decision tree model I can build. Okay. And finally, this is clustering, which is the unsupervised model. Okay. Again, this came from the YouTube video example. Okay, now let's say I own a pizza shop. Okay, and these are my potential customers. Right, and now I have 3 motorcycles, like those delivery takeaway motorcycles. And I have to find the best spot to ask the driver to stand by and wait for orders. Okay. So how do the machine find out where are the best spot? Let's say the machine, firstly have 3 random spots. Okay, just randomly allocated 3 locations on the map. Okay, the next thing the computer do is go through every single dots and see which driver is the closest one. Okay, let's say I go to this dot, because the red one is closer, I just paint it as red. And let's say for this dot, compared to the blue and the red, it's closer to red, so I just paint it as red. Okay, now I have 3 groups. But if you look at it carefully, it's not very optimized. Okay, if I draw 3 groups, I'm gonna draw like 1, 2, and 3. And the optimized position should be like in the center of the cluster. But in this case, it's not optimized. So what the model does is it moves towards the center of its colored group. Okay. So basically from this position to this new positions. Okay. And then at this point, it goes through every single dots and redo the process. So we redo this process, which is going through every single dot to see which one are the desired color. So it goes through these blue dots, but now the yellow one is closer to the blue one, so you paint it to yellow. And for this guy, the blue one is closer, so you just call it paint it as blue. And after it repeats the process, it keeps changing the center point of the driver. And eventually, okay, this is like the second steps. So now you have this, and then you paint these as blue, and then we allocate this red driver to the center of these dots, and eventually you have placed the driver in the most desirable positions. And you also successfully classify the three types of dots. Okay, and this is called the k-means. What means by k? It's the number of groups, number of cluster you place. And what means by mean is just going to the average positions of the dots. Any question with this example? Okay. Alright, so we went through a lot of algo today. So this is just a map to help you to make a decision on which model you have to choose. Okay, you start from sklearn, and you have a lot of split, like Okay, if you have more than 50 samples, it's okay to keep going. If you have less than 50 samples, you have to gather more data. And then you ask yourself whether or not you want to predict a category or a magnitude. If it's a magnitude, you go to regression. If it's a category, then they'll ask you like whether or not you have a labeled data, do you have the ground truth or do you not have the ground truth? If you have the ground truth, you go for a classification, which is the decision tree. If not, you go for a clustering, which is the k-means. Okay? And there are a lot of different models within every main group, but we're gonna go through it later on. Okay. Okay, and this is this is a layout of which are the most powerful model. Okay, there's a research paper that take 158 very different sample sets and try to apply different model and compare the prediction, which one predicts the best. Okay, and out of all the models, gradient tree boosting outperform almost every single other model. What's below gradient tree boosting is random forest, which is an improved version for decision tree. And the linear regression is not even on scale. We have okay, not this one. Oh, okay, we have logistic regression, which is very similar to linear regressions, but you see it got outperformed almost all the time. So now you might wonder why, okay, if that's the case, why not every time we use gradient tree boosting? Okay, because it works the best. So why don't everyone use gradient tree boosting? Can you think of a reason? It's not slow. It's quite fast.
Too many variables to
Sorry?
too many variables to
Oh, that's part of the reason. But the main reason is it tends to overfit. What's mean by overfit? Is mean it get too biased to your training sets. Okay, so let's say you train the house price in Hong Kong. Okay, now you get a Macau house price and ask the model to do predictions. Okay, in a linear regression, probably there's some degree to generalize the Hong Kong case to Macau. But for gradient tree boosting, it tends to fit the data very well that you can't really generalize to other cases. Okay. Yeah, the other thing is gradient tree boosting is like a black box. Okay, it's just like a magic box that no one really understands what's going on inside. So if you want to explain to someone about prediction, it's very hard because you can't really explain why do you come up with these predictions. Okay, but if you don't really care about explanation, all you care is the accurate predictions, then you can always use gradient tree boosting. Okay. If you go on Kaggle and then just do XGBoost. Okay, and you will probably somehow see an article say every single winner in Kaggle uses XGBoost. Okay, because a few years ago, XGBoost is not that popular. But then people somehow figure out everyone that wins on Kaggle uses XGBoost. And somehow XGBoost got very popular. Okay. But we're gonna teach XGBoost later on.
Just one question.
Yeah.
So, according to your experience, which the table effect is which result into prediction?
Yeah, personally, I would always go for a random forest because okay, basically decision tree, random forest, and XGBoost is one family. Random forest is just a randomized version for a decision tree. So if you think of it, a lot of trees makes a forest. So random forest is actually a lot of decision trees, but you randomized the sample and the number of variables. So let's say you do 1,000 decision trees, but every time you shuffle a little bit about the variables and the samples. And so every tree is a little bit biased towards part of the sample. And now when you do a prediction, you ask every single tree what's the outcome. And you ask them to vote for the majority. So it's like a majority vote within the trees.
So it is to do with classification.
Yeah, it's a classification.
How about for the magnitude?
The magnitude. Actually, random forest can do regression as well. So if you think of magnitude, you can put categories into magnitudes like a bucket. So let's say you slice the magnitude to every 0.1. So that means you have like from 1 to 10 you have 100 categories. So you can put it into a categorical problem. Okay.
So you try to by using it. If you want to use the random forest, you frame magnitude problem to classification.
Yes, you can try a random forest regression and go to sklearn. Okay, I forgot to talk about this sklearn websites. So this is the most popular machine learning library on Python. Every single model that I mentioned can be found on sklearn. So there are a lot of examples on sklearn. This is a case that you have to classify a nonlinear shape, which can't be done in a linear regression. Because linear regression would probably plot a straight line and classify the two groups by everything below this line is group number 1, etc. But if you do it in using different model, it can classify it properly. Okay. Anyway, let's go back to our linear regression. So, okay, for linear regression, it's a lot to do with getting a correlation between two sets of data. And in this case, computer is a lot better than human. So let's say, given this data, the game now is to ask you to guess what's the correlation between the two. And you can just randomly give a number like 0.4, and you can guess. And the true correlation is 0.45, and you can keep going. I'm quite good at this test because I look at this kind of graph every single time. So now my error is 0.01, and you can, I think this is like 0.23. Okay, now my error is quite big. Okay, if you keep on playing this game, you can know you're not very good at finding the pattern between the dots. But computer can always try the best fit line for millions of times and find the best possible line. Okay, I'm not going to read the entire entire paragraph, but all you need to know for a linear regression is it has 3 components. One, this is the response, which is the ground truth. We have the intercept, and we have the coefficients times the variable, which is something like y equals mx plus c, which you should learn in your secondary schools. And okay, I'll see. Okay, this is another very interesting dataset. You have all the car models, and you have all the features, like how strong is the horsepower, what's the specs, what the like the oil per, how much oil do you need per miles, etc. And you have all the different costs. Okay, if you plot it out, you can plot 2 variables this way, like mpg versus the weight. Okay, it means the lighter the car, the less oil it requires. Okay, and then let's say I want to do a linear model given the weight. I want to predict what's the mpg. Okay, and after you run the model, it gives you 2 numbers for the coefficients. And what this 2 number means, it's y equals mx plus c. I think it means weight times weight times, I forgot, minus 5.34 and plus 37 equals the mpg. That's what this actually means, the coefficients. Okay, again, it's the straight line y equals mx plus c, and the coefficient is basically the slope of the line. Okay, I did it correctly. Okay. Okay, you also have something called the score of your regression model, like how nicely it fit. So that's the R square. So usually the higher the R square, the better the fit is. But it is not necessarily you have to aim for higher R square, because sometimes you don't have enough variables to get a score of 0.9. Okay, it's very rare to have that much predicting power. All you care is to improve the R square, and usually the higher the R square, the better the predictive power.
So that is to show the R square.
Yeah.
Regression models.
Yeah. But actually, if you do machine learning, not many people look at R square. Because the main difference is, if you're a scientist, you care about the reasoning behind. Okay, you care about how this variable contribute to this outcome. I think for psychology or for some other proper like biology studies, you care about the relationship. But for machine learning, all we care is to make the right predictions. So we don't really care how bad or how nicely it fits, as long as the prediction is very close to the truth. Okay. And if you run it, this is the best fit line the computer finds. And it finds by plotting out the train predictions. Okay. I think this is less interesting. Okay, let me have a look. And if you want to learn more about regression, I would recommend this video, which is, I think it describes it and explains it quite well.
All right, so now we're at least going to
okay, the last example I'm going to go through is a very famous example. Like every machine learning practitioner will have to use this dataset. It is called the iris dataset. Okay, I will just do iris dataset. Okay, iris dataset is basically three type. I think it's not three type of flowers, but they are the same type of flowers, but they have a different stage or different variation of the same type of flowers. And scientists somehow care about how to differentiate the three, and they differentiate the three by measuring the width and the height of the flowers and how tall the shape is, I think. But somehow this dataset is famous because if you look at the length, width, it doesn't really tell you much. This is a ground truth of the type of flower, the species. And for a naked eye, you look at the pattern, it doesn't really make any sense. So it's very hard to classify the three. But somehow if you go below, okay, if you look at the pair plot, you can see the three groups somehow can be classified in very different dimensions. So the first two can be classified nicely in this case, because this is quite further apart. And maybe in this case, control line right here to classify these two cases. Okay. And then Let's go back up. Alright. Okay, this part is just to show you exactly what happens inside the algo, which I don't think you should care about right now. All you care is how to apply it. Okay, so to apply, to fit a regression line in this data sets, just basically split it into x and y. Remember the train x, train y, and then just fit it into a model, and this should give you the ground truth. And then okay, I think because these are more related to the next class, so I think I'm going to talk about it next class. So the only homework for today is to read this. So we have another very famous dataset in machine learning called the Titanic datasets, and it is on Kaggle. You can compete on it, and this is just an article to teach you how to get the highest score in this exercise. Okay, so the homework is just to read. Okay. Any questions for the class?
So what differs from a expert AI programmers to a
Yeah. So you can tell the process is very simple. Just split the data and fit it into a model.
Yeah.
So I think there are three qualities from differentiating like expert and beginners. First one is where do the data come from? Okay, you have to figure out a way to get the purest data and to get the biggest amount of data. That's number one. Number two is which model you select. So you see there's a lot of different model. Some applies better in some cases. And it's really down to your knowledge to pick the right model at different time. And thirdly is the parameter tuning. Okay, like for XGBoost, parameter tuning. I'll give you an example. Okay, not this one. If you go back to my first, this one. Okay, these are the parameters. N estimators equal 100. Learning rate equals something like this. We have gamma. Probably doesn't make any sense to you. And then these are the parameters. And somehow there are a best combination of these numbers that gives you the best predictions.
Is it like black magic?
You
need to know pure math.
You don't really, but I think you have to understand the model to know which parameter to place. In many cases, it's just try and error. But because you have so many parameters, you can't try every single combinations. Yeah. Okay. Any more questions? Okay, if not, thank you very much. I'll see you on Thursday.